Okay, today we are going to introduce in this lecture briefly subgroups, and we'll just talk a little bit about them. Here, so this is a subgroup. So the definition of a subgroup is pretty simple. A subgroup is a subset of a group that is also a group under the same operation. So if a subset H of a group G is itself a group, and here this is underlined under the operation of G, we say that H is a subgroup of G, and we write H, and we use the same as the less than or equal to sign to indicate that H is a subgroup of G. So of course we're used to using that symbol when we're dealing with comparing numbers, comparing real numbers, but here we're talking about groups. Just an example, the group of 6 matrices, or as I like to refer to it, the group of that I made that mistake in labeling C. So we had A, B, C, D, K, and then the identity I. And then H, remember initially as a 3-element group I used A, I didn't use B, I think I used B and D and I. Then H was a subgroup of G. Definition, if H is a subgroup of G, but it's not the whole group, we say that H is a proper subgroup of G. And we may write H, use the greater than, strictly greater than sign. Though really, I've seen in textbooks, that's maybe a little bit less common than this notation for a subgroup. And then just the fact, in any group G, the identity is a subgroup of G, and that's called the trivial subgroup. And also a subset of any set is a subset of itself, so G is also a subgroup of G. So you've got the smallest possible subgroup of G, just the identity. The largest possible subgroup of G is G. Anything in between. That's kind of what the subgroups look at. When you analyze what the subgroups are, you certainly, at biggest subgroup, you've got G. Smallest subgroup, you've got just the identity, a one-element set, a one-element group. What about in between? Let's get we had an example, let's get a non-example going with that operation idea. So a non-example, if G is, say, the rational numbers under addition, and H is the positive rational, so all x in Q such that x is greater than 0 under multiplication, then even though H is a subset of G, G is a group, H is a group, H is not a subgroup of G. Because H is not a group under the same operation as G. We've got different operations. So when we say a subgroup, it's not the subset that's a subset of a group that's also a group under the same operation. So as you go through homework 1, there's a couple of instances I asked you to prove something is a group. And a couple of examples that I've done here to see it's a group. It's usually a longer process. So somehow there's an idea if you have a group, how can you prove something is a subgroup? What's a shorter way? So there are these subgroup tests. So that's what I like to do now. I like to maybe prove 2 subgroup tests. So we'll call one theorem. And I call this subgroup test 1. It's sometimes called the 2-step subgroup test. So let H be a non-empty subset of G. So then here, so let me be clear, this is not a greater than or equal to, it's a subset sign. So it's a non-empty subgroup of G. Then H is a subgroup of G if both the following 2 things happen. For all A, B in G, the product of A, B is, for all A, B in H, the product of A, B is in H. And you also need B for A in H, A inverse A in H. So this is subgroup 1. This is really subgroup test 1. So let's prove this subgroup test. And I'll just say certainly associativity holds. Right? For any three elements in the group G, we have the associative property. So in particular, since H is inside of G, for any three elements of H, we have associativity. We have the associative property. Basically, if we have for any three elements in the group, we have this equation, which is true. That certainly implies for any three elements in the small set H, we'd have that equation. What about the identity? Well, we have an identity in E. Be the identity. And that meets the identity property for every element in H. Every x in H, xe is equal to x, and ex is equal to x. But we have to show that E is an element of H. Well, why would E be an element of H? H is not the empty set, so it's got some element A in it. By the property B, A inverse is in H. By the property of A times A inverse is in H, or E is in H. Thus, H has an identity. So we've got associativity, it's not empty, it's got an identity. Is a binary operation closed? Remember, the guarantee is that A, B, for any element in H, for any two elements in G, their product is in G. But by assumption A, right here, H is closed under the group operation. And again, A has an inverse, A inverse, and by property B, each element of H has an inverse in H. Right, again, take A and H. It certainly has an inverse, A inverse. But for the identity for the inverse property to work, A inverse has to be in H as well. But that's exactly the second assumption, B. So that concludes the subgroup test. If you want to show a group is a subgroup, you can just show these two properties. And also, you have to show it's non-empty. Sometimes this is called a two-step subgroup test because you have to show two different things. You first show that the product of two elements in H is in H, and then you have to show that given an element of H, its inverse is in H. So there's two things. There's really a third thing you have to show. You have to show that H has to be non-empty. And then there's some more details in the about this in the notes, but that's pretty much it. So that is a proof of these two subgroup test one, two subgroup tests. a two-step subgroup test. Let's get a different subgroup test. And maybe instead of notations, I'll just say the word. Instead of putting this notation, I'll say, let H be a non-empty subset of a group G. In fact, actually, if I go back to here, I should have stated that let G be a group. So actually, the way that subgroup test was written, I left out that important fact. You need to have a group G, right? Obviously, without a group, you know, how do I pull out this associativity property? Why does G have an identity? Why is there an inverse? And that's, again, the assumption is not just that you have a non-empty subset H of G, but that G itself has to be a group. Then H is a subgroup of G if for all AB in H AB inverse is an element of H. This is sometimes called the one-step subgroup test. Even though far from having, you don't just have to show one thing, but you have to have a non-empty subset. But if you have a non-empty subset, you can show that if you have a non-empty subset of a group G, then all you have to show is for any two elements in H, the product of an element in H times the inverse of that second element in H. If that product is in H, that's enough to show you have a subgroup. And this is usually a little bit quicker. Obviously, you just have to show one thing instead of two, but sometimes some students in some cases prefer the two-step subgroup test. Maybe it's just easier to show this fact and show this fact rather than showing two facts at once. So you're really flexible. Either way, they're both valid tests. So let's prove this second subgroup test. So I'm erasing this, but again, if we go back, make sure to include this assumption. We have to add that G is a group in this assumption for the subgroup test. So let's prove this. So again, the associativity of multiplication in the group G implies the associativity of the multiplication in H. Just like before. And also as before, H is not empty, so there's some element A in H. Then what do we have? Then, if we look at then, in particular then, for A and A in H, so think of A being as B, one element and two element, A times A inverse is in H, or E is in H. So we have the identity property. Yeah, maybe it looks like a fast one, maybe it looks like, wait a second, did I assume that the inverse of A is in H? But look carefully at the way the assumption is. What can we conclude? If A is in H and A is in H, it's the product of an element of H times the product of the inverse of any element of H is still in H. Well, if A is an element of H and A is an element of H, so the product of A times the inverse of A is in H, but now we have the identity in H. So we've got that. What about to show A inverse is in H? Well, now we've shown E is in H, so since E is in H and A is in H, we have what? We have E times A inverse, the product of an element of H times the product of the inverse of an element of H has to be in H. But E is a two-sided identity, so A inverse is in H. So we've got the identity property and we've got the inverse property. Associativity as follows for given. What do we next? The only thing left to show is closure. To show closure, let A and B be any two elements of H. What we've just shown before we know the inverse has to be in H. Because I've just proved, right? Given any element of H, its inverse also has to be in H. Right here, in this argument here, this A, there was nothing special about this element A. The inverse of any element in H is now in H. So A times the inverse of B inverse is in H. Claim. In a group G, the inverse of G inverse is just equal to G for every element. Let's assume the claim is true. So then A times B inverse is in H means A times B is in H, and we have proved closure. Thus H is a group, and so a subgroup of G. So I'll prove that claim in a second, but if we take care of that claim being true, we've done everything, right? Again, the associativity we inherit from G, it's not empty, so we're able to show that the identity is in H. Once we have the identities in H, we've shown that any element, for any element A, the inverse of A is in H. But that allows us to then show the closure of H if we can show that B inverse is just B. I think I might have shown that when we talked a little bit how the properties of integers with exponents, the property of integer exponents, I should say, holds in this abstract group notation. But let's look at, let's prove this claim. And the proof of the claim is real easy. We have G inverse times G is equal to E. Think of this as being an element. And G times G inverse is also equal to E. So that means think of this as being an element of the group. The inverse of G inverse is just G. Right? Multiply G inverse on the right by G. I get the identity. Multiply G inverse on the left by G. I get the identity. That means the inverse of G inverse is just G. That's the element that works. So let's look at an example. Consider Q under addition. The integers Z is a subgroup of Q. So we use the one-step subgroup test. I call subgroup test 2. Well, Z is certainly a subset of Q. And the integers are not the empty. There's infinitely many integers. There's a bunch of integers there. -8 is there. -12 is there. 1/3 isn't there, but certainly there's a bunch of stuff in integers. So, what does A B inverse become? Think about that. That's really A combined with the inverse of B. Well, what's the operation? Here the operation is addition, and the inverse would be negative. So this is really A, B inverse, in this case would be A plus the negative of B. Again, it's sort of in an abstract group, we'd write A, B inverse, like here, the product of A and B inverse. But now in this specific example, the operation, the group, if you will, multiplication, the group operation is addition, and the inverse is the negative of a number, so A plus negative B. So then, for all, instead of A and B, I'll use M and N and Z. M plus a negative N is just M minus N. That's certainly an integer. And so Z is a subgroup of Q with addition as the operation. We'd also say Z is a subgroup. Z is not just a subgroup, but a proper subgroup of Q. Because, as I used an example earlier, I forget what I said, 2/3 or whatever, there are certainly rational numbers that are not the integers. So it's a group, it's not the whole group. And Z is not a trivial subgroup. Just the single element set 0 under addition is the trivial subgroup. Again, that's because multiple under addition, the identity under addition would be 0. Which is why the inverse of an element is its opposite sign. Okay, we'll now define a subgroup for each group has at least one special subgroup. But we're going to take a brief break now, and we'll pick up this lecture at a later point.